So here we're going to start talking about a different way of modeling a categorical response, and that is if we have a quantitative explanatory variable. So what we've been doing up till now is if we have two categorical variables, a quantitative response and a categorical explanatory and a categorical response variable. But now if we've got a categorical response and a quantitative explanatory variable, we're going to be back in the regression realm, specifically talking about logistic regression. So the example we're going to talk about is using age to predict the probability of subscribing to a newspaper. And the issue here is that you either subscribe or you don't. So our response is kind of like an indicator variable where we've got 1 if you subscribe, and that would be a success. I cannot spell today. So 1 if you subscribe, and 0 if you don't subscribe, which of course would be a failure if you are the publishing company. So here's what the data might look like if we were to plot it, and if we were to do a linear regression model. So we have all of our successes up here, all of our subscribers up here at 1, and then all of our failures or non-subscribers down here at 0. So it's not a very interesting scatter plot, but it is a scatter plot nonetheless. And we can see that as people age, we tend to see more subscribers, and the younger people tend not to subscribe. So there is a bit of an association, and we'd like to describe that relationship. So if we fit a linear regression model, we would get something like this, where pi, that probability of success in the population, equals alpha plus beta x. But we also can see maybe there are some issues with that. So we get our p hat, so this is our model. So our sample prediction equation is p hat equals negative 0.750 plus 0.028 times age, which is x. And so let's figure out where this problem might be. So I'm going to pick two ages. So we're going to try at age equals 40 and age equals 65. So 65 is a little beyond the bounds of our data, but it's also a totally reasonable age to try to predict at. So it's a little bit of extrapolation, but it's not way out there. So let's see what happens. So at x equals 40, we just plug 40 into our prediction equation the same way we would always do. So p hat equals negative 0.750 plus 0.028 times 40, and we get a value of 0.25. So this is our predicted probability of subscribing. And then we do the same thing for 65-year-olds. So at x equals 65, p hat equals negative 0.750 plus 0.028 times 65, and that gives us a probability, or p hat, of 1.07, and we can see where the problem lies. Now we have a predicted probability of subscribing that is greater than 1. This is impossible. We know that probabilities, predicted or otherwise, have to be between 0 and 1, so this is not a valid prediction. And this is not just because of extrapolation, but this is the problem that we get when we're trying to predict probabilities using a line. So what we want to do instead is not use a linear model. We're going to use what is called a logistic regression model. And a logistic regression model is now an S-shaped curve for predicting the probability of success. So when we had our linear model before, we had the probability is alpha plus beta x. It was a linear form. We had the same change in the response on average, no matter where we were on our x scale. But now, as S-curve, we're going to see a different change in the response depending on where we are on that S-curve. Right? So we're going to have the same change in x, but a different change in Y, our probability. So, what does that look like? Well, we still see something a little familiar. We still see this A plus beta x, or alpha plus beta x for that population, but it's now in an exponential. We now have e raised to alpha plus beta x, and we see it repeated down here in the denominator. And so this new form gets us that S curve. So we're modeling our probability using this kind of funky thing, but because of this relationship, that probability will never be less than 0 and never be greater than 1. Do you have to memorize this? No, but this is what goes on in the background when we do logistic regression. So, having done this, using this logistic regression model, I can now instead get a new intercept, A, and a new, what I'm going to call slope, but in heavy quotation marks, B, that's going to give me this S curve instead of that line. And we can see that it's never going to go above 1, and it's never going to go below 0 because of that nice smooth S. So now let's get our predicted for people who are 40 years old. So at x equals 40, p hat is now going to be based on this prediction equation. So p hat is going to be e to the negative 5.888 plus 0.131 all over 1 plus that same thing, e to the negative 5.888 plus 0.131. And that gives me a predicted probability of 0.343. So this is my predicted probability of subscribing for 40-year-olds. So if I have a 40-year-old, I'm going to give them a chance of subscribing of about 34%. So what are some cool properties of logistic regression? This is going to get a little mathy for a second, but bear with me. When e, so this is in the population, when e to the alpha plus beta x equals 1, what does that do to this whole thing? Well, if e to the alpha plus beta x equals 1, then I've got these two terms equal to each other. That means that pi equals 1 over 1 plus 1. That means my probability of success is 1/2. Cool. So if I can figure out what gives me 1 does e to the alpha plus beta x equal 1, then I can figure out when I've got a 50-50 chance of success. But there's something we know about e to the x. E to the 0 equals 1. Anything to the 0 equals 1. So I just need to figure out how to get 0 in that power. Alpha plus beta x is this power. So alpha plus beta x equals 0. That just means beta x equals negative alpha. And I'm going to do my algebra to solve for x. Oops. So when x equals negative alpha over beta, that's going to give me e to the 0. And when I have e to the 0, then I've got a probability of success of 1/2. So in sample data, I've got a predicted probability of success when I've got negative a over b. In this case, my predicted probability of success, sorry, I wrote that wrong. My predicted probability of success is 1/2 when x equals negative a over b. In our data, that means when x equals negative 5.888 over 0.131, which is 44.5. So when we are dealing with 44-and-a-half-year-olds, they have a predicted probability of success of subscribing of about 50-50. So right about here, 44.5-year-olds, they have a 50% chance of subscribing to the paper, but they also have a 50% chance of not subscribing to the paper. That's basically our make or break point. That's the point where we say there's a 50% probability that we're going to have subscribers, and then about 50% of 44.5-year-olds are not going to subscribe. After they hit 44.5 years old, then we're going to start to see people subscribe at a higher probability than 50%. And then people who are younger than 44.5 years old, those are the people who are subscribing less than 50% of the time. Then fewer than half of those people of those ages are subscribing. This is also the point at x equals negative alpha over b is where we get the biggest change in the predicted response. That is, this is where the slope is the steepest. So if I look at a change in the response here, I'm going to have a big change in the probability, as opposed to if I compare down here at around 25 or up here at around 50. Just like we saw for regression, for linear regression, we can also do inference. And all this is going to do is tell us how strong is the evidence that a relationship exists. So our null hypothesis is that beta, again, that slope in heavy quotation marks, is 0 versus versus non-zero. So if the slope really is exactly 0, that means there is no association. In this case, we're talking about association between the true probability of subscribing to the paper and age. The alternative is that there is an association. Our test statistic here, this is going to be a z-test, and we can tell that this is going to be similar to what we've seen before because we've got a statistic minus a parameter, and this parameter value comes from the null hypothesis over the standard deviation or the variability of that statistic. So this is going to be z-obs equals our sample slope minus the hypothesized value, which is 0, over the standard error of our sample slope. In this case, our sample slope was 0.131. The hypothesized value again was 0. And if we go back to our output, we can see that the standard error of that slope was 0.054, giving us a z-score of 2.519. This is a medium-sized z-score. It's bigger than 2, it's less than 3, so it's big but not huge. If we were to look at a z-distribution, we would find 2.519 close to the tail, but not way out in the tail. Because this is a two-tailed test, we have to look in both tails to get our p-value. And it turns out that p-value is 0.0118. There is strong evidence of an association between the probability of subscribing and age. Now, this does not tell us how big that effect is. It does not tell us how steep we can say that slope is, or how quickly that instantaneous rate of change is at p hat equals 1/2. It just tells us that the slope is not exactly equal to 0 at p hat equals 1/5. Now, there are, just like with any other model, assumptions that are required to make this test valid. Right? So you should not run this test, and you should not use logistic regression inferential methods without taking a more advanced statistics class like Stat 4230 so that you can better understand what those requirements are. But you'll probably see results like this, and so what I want you to do is focus on understanding what these results mean. So what does it mean to have a categorical response when you have a quantitative predictor? What are we actually doing when we interpret these results? And so with that in mind, let's look at a multiple logistic regression model where we might have more than one explanatory variable predicting a categorical response. In this example, some researchers explored the effect of tracking, among other things, on the likelihood of a student receiving an IB or an International Baccalaureate diploma. So a variety of models were investigated, and by that I mean there were a lot of variables looked at and investigated, but the final model had just 3 included, and those 3 are the aptitude, special ed, or SPED, and pre-post. And pre-post, this is the tracking variable. So aptitude here is considered to be quantitative. SPED here is categorical, and pre-post is categorical. And just like we saw with linear regression, if you have a categorical variable and a regression model, you have to make them indicators. So this was created, an indicator was created. And so here also an indicator was created. And so for pre-post, the indicator was 1 for D-tracking. And that just means all students were placed together. That is, they were not tracked. And 1 if they were tracked, or 0 if they were tracked. And that means that they got separate classes. Right? Here we have the results of the model selection process. And so, as I said, we have a whole bunch of variables that were considered, and through one model selection process, and we've talked about how model selection is not always a great thing to use, the final variables that were chosen were these 3. And so we can see that there is strong evidence that aptitude is useful when SPED and pre-post are held constant. There is weak evidence that SPED is useful when aptitude and pre-post are held constant. And there is strong evidence that tracking is useful when SPED and aptitude are held constant. And I'm basing that just on the stars. We do not have what the actual p-values are in this case, but we can find them because we know how to calculate the z-scores and get the p-values from them. Right? So let's look at the rest of this. So for example, we have a whole bunch of terms that are not included in the final model. They were tested, they were found not to be useful, but they're still telling us, they're still giving us that thorough reporting so that we know what had been considered but just not included. So these are all, for example, interaction terms considered for the model, but had been dropped. Similarly, all this pre-post by aptitude, these are more interaction terms. They had been tested and it was determined that they were not useful. Right? So, some things that we see. The estimated effect of aptitude on the probability of getting an IB diploma. So this is B1 is 1.82. We see this is greater than 0, so we see that there is a positive association between aptitude and obtaining the probability of obtaining an IB diploma. Cool. We see for pre-post, B3 equals 0.54. This is also positive, but this is a categorical variable. So there's a positive association between obtaining, between being detracked and obtaining the IB diploma when the other variables are held constant. So coming over to the plot, that helps us understand what that means. So a positive association, so that means relative to being tracked, students who are detracked have a higher estimated probability of success, right? So this is comparing groups. All right, so we can see that. So here we've got the tracked groups are the small dashed lines, the detracked groups are the big dashed lines. And at every fixed level of aptitude, so holding aptitude constant, we always see that the detracked groups are doing better on average than the tracked groups. That's what that B3 greater than 0 is telling us. It tells us that those two slopes, the slope or the curve for the detracked group is going to be higher than that for the tracked group at any fixed value of aptitude. This positive slope here for aptitude is telling us that we're going to have an S-curve that as aptitude increases for any fixed value of pre-post for the tracking, we're always going to see that for any fixed value of aptitude for any fixed value of tracking, that as aptitude increases, we're always going to see an increase in the probability. So that as aptitude increases, probability also increases. What would an interaction between aptitude and tracking look like? So if aptitude and tracking interacted, what would these curves look like? How would this change? An interaction in simple linear regression, an interaction meant that the slopes of our curves, of our lines, change. So an interaction here would also mean that these lines or these curves would change. So that means the effect of one variable changes with the levels of the other variable. So here we would still have aptitude, and we would have two curves for tracked and detracked students, but we might see something like this, where here we've got the detracked students, and we might see something like tracked students. So that would just mean that the effect of aptitude is different for one group of students than for the other. It of course would probably not be this extreme, but that's just to illustrate the point that the two types of students, those who are tracked and those who are detracked, would have different slopes or different curves. So the effect in this case is how steep or how tight that S is. This is one way that might look. So that's the end of talking about logistic regression. We will pick up in our next class thinking about the logic of regression and nonparametric inference.